Well, good afternoon, everybody, and welcome to the third of today's webinars from Smart Vision Europe. We're going to finish up today talking about regression techniques in SPSS. We're going to look at linear regression, logistic regression. And my name is Jarlath Quinn, and I'm one of the data analysts and consultants at Smart Vision. I'm joined online today by my colleague, Rachel Clinton, who'll just be making sure that everybody's logged in correctly and keeping an eye on the questions as we're going along. If you haven't joined any of these sessions before, you should be aware that we do record them, so you'll be able to listen to the session again afterwards. And there's a bit of slideware here, which just used to introduce some concepts. I will email a link out to you afterwards so that you can download the materials once the session is ended. With regard to colleagues who are unable to attend, if you think it might be useful for them, if you get enough of them together, it may be possible for us to arrange a rerun. The best thing to do is just reach out and ask us, send us an email, something like that. And with regard to asking questions, all the lines are muted, so we ask you to use the chat panel. I'll try and keep an eye on it as I'm going along. But if we run out of time, we do, as I always say, we always get lots of questions sent by email afterwards. People have, when they have a chance to digest what we're talking about and have a think about their own work and manage to apply what they've looked at here, they may well send us a question afterwards, and we can take time to try to answer it thoroughly for you. So don't be afraid to do that. With regard to who Smart Vision are, we are a gold accredited technology partner to IBM, as well as Predictive Solutions and Data Robot, and we specialize in data science, machine learning, advanced analytics, statistics. That being said, we do work with open source technologies such as R and Python and Spark. We're made up of a team of people who've got a lot of deep experience within the analytics industry. I worked for SPSS for a long time and SAS and IBM as a consultant. And that means that we've all got pretty deep experience of applying advanced analytics and statistics and machine learning and data science and AI and all that sort of stuff across many different sectors and many different applications within those sectors. And of course, one of the applications, one of the techniques we would have used on a regular basis are stuff to do with different types of regression. So today we're going to be giving an overview of different regression techniques and how to explore linear relationships. Those of you who were attending the correlation session that we had earlier this morning, there will be a little bit of overlap with that, only very briefly, so forgive me for that. But for those who haven't attended that session and want to come to linear regression session, then we really need to talk about correlations a little bit. We'll talk about performing a simple linear regression and then move on to multiple linear regression to make predictions, and finally predicting response probability of logistic regression. So the first thing we want to establish is the fact that the term regression, people say, oh, I used regression. It's actually a generic term, so it could refer to lots of different techniques. It's a family of statistical techniques used to predict outcomes and generate estimates and model the effects of variables across hundreds and hundreds of different applications. So the key point here is that linear regression is used when the outcome is continuous or scale data in nature, so where it's a number field, not a category field, and where the relationships between the fields can be described using straight lines. So you can use straight line relationships. Quadratic regression is a variant of linear regression. It's used again when the outcome is continuous, but the relationship to the dependent variable isn't a straight line. It's more of a curvy linear relationship that's known as a second order regression sometimes. Logistic regression is used when the outcome consists of two categories. That's called binomial logistic regression or binary logistic regression. Or when it has more than two categories, it's known as multinomial logistic regression. And we also have, as anybody who looks around our site and looks at our YouTube channel will see that we do have a number of videos that look at different types of regressions, not just linear regression, things like quadratic, but also Poisson regression. Poisson regression is commonly used when the dependent is continuous, but where it's recording counts of events. So it tends to be things which don't occur that often. It would be things like the number of insurance claims that are made over the course of a policy, or the number of visits to, I don't know, visits to hospital over the course of 10 years or something that somebody might make. So it's a special case and of regression. And again, we have some recorded videos if that sounds like something that might be useful to you. So where are regression techniques used? Well, they're used where we're trying to model the relationship between things like promotion, spend, and revenue. So we want to know if we spend a lot of money on promoting something, and we've got some historical data around that. We can estimate how much money or how much revenue we're going to generate. I've done projects where we're trying to estimate things like pollution levels in the sea or in inshore areas or in estuaries following heavy rainfall or rainfall patterns in the surrounding areas because that tends to wash down things like nitrates and fertilizers and stuff like that from the fields, which can cause rainfall. Can cause pollution. Or things like predicting tourism revenue based on exchange rates and air travel costs for a given area. Cost of air travel can have an effect on it. Exchange rates can have an effect on the number of tourists they're going to get. Predicting student test scores based on that student's previous test results and the peer group performance, the way in which the rest of the class is performing. Estimating website hits, visits to a website based on things like social media retweets, or people sharing media content across different platforms, or even things like predicting sales of barbecues based on temperature forecasts. You can actually do that, and supermarkets have a pretty good idea of how many units of barbecue they're likely to sell over a warm bank holiday weekend, and indeed how many tubs of ice cream and stuff like that, because temperature is such a strong driver of those things. But these are all potentially linear regression models that we could run. They're all very different from one another. The interpretation would be the same from one to the next, even though the examples would be very different. So regression itself, the term regression itself comes from regression to the mean, which just means basically regressing towards an average, an overall average. Um, the mean that we're talking about is usually referred to as the line of the least squares. And it's simply the fact that you can put a line through a relationship that's described by a scatter plot. And if you try to put the line through it in such a way that you're minimizing the distance between the points in the scatter plot, the actual data points, and the line itself, you end up what's called the line of least squares. So the line of least squares, because they tend to measure the squared differences between them. Why do they measure the square differences? Well, because if you think of the line as the kind of overall average, the mean, the regression of the mean, then some points are going to be above the mean. There might be three units above the mean. Some might be 3 units below the mean, and that'd be -3 instead of +3. And obviously, if you add those all up, they'd come to 0. So we tend to square the differences, and -3 squared is 9, and +3 squared is 9. So it tends to be that you're trying to minimize the squared differences. Hence, it's called the line of least squares. And this line is actually literally the regression model. And the formula for it is the same as the formula for a straight line. But that's the concept. That's the idea of it. That's how it's created. It's a kind of average of the relationship between, in this case, two variables, which is the percent of people who are reliant on public health care. Each of these is a US county, each of these data points, and the percent unemployed. And so as we can see here, that the higher the unemployed percentage, the larger the percentage of people who are reliant on public health care. Now, the key here about this line, as we pointed out in the correlation webinar earlier on, was it is just an average. The line is just an average, just like anything else. There's nothing special about it. And that means that you can end up with exactly the same line, even though the data looks very different from one case to the next, because the line is simply a straight line, it's an average. It doesn't really take account of the shape of the relationship. If it's curvy linear, for example, it is influenced, as one can see, because it's an average, it's influenced by extreme values in the same way that if you were to calculate average height of students in a class and somebody walked in who was 8 feet tall, if it's only 30 students in the class, something like that, then the average height is going to go up quite a lot due to an extreme value. And even when you get binary fields, just here we've got just two values of 8 on one person who's a value of 20, it'll still produce the same straight line. So exploring the data beforehand to make sure that it's kind of that you understand why the line is being formed or where it's likely to be formed is a good idea. It's good practice. Now, one of the ways in which we measure the relationships, the strength of the relationship between these factors is traditionally we use something like correlation values or Pearson correlation values. And Pearson correlation values run from two extremes. They run from -1 to +1, with zero in the middle. And the closer they are to either -1 or +1, the stronger the linear relationship. So here we have a scatter plot showing automobiles, and the automobiles, we've measured their horsepower and we've measured their weight. And we're finding, as you can see, that pretty strong relationship between horsepower and weight of the vehicle. Horsepower, of course, would be dictated somewhat by the engine size, and the engine size contributes a lot to the weight of the vehicle. So you can see that's quite close to 1, so it's a strong linear relationship, 0.859. A weaker linear relationship only has a correlation value of 0.434. And here we can see one where we're looking at the relationship between time to accelerate from 0 to 60, acceleration speed, and miles per gallon. We're finding that, yeah, there is a linear relationship here. It's not as clearly defined as the previous one, but generally speaking, if the car takes longer to accelerate from 0 to 60, it tends to do better on miles per gallon, it tends to be more fuel efficient. And then we have a negative relationship, one where it's going the opposite direction. It's still a strong relationship. It just happens to be negative in the sense that as one value goes up, the other value tends to go down. So we have a relationship between horsepower and time to accelerate from 0 to 60. If it's got a lot of horsepower, then it can accelerate very quickly, maybe less than 10 seconds from 0 to 60. Um, and if it takes a long time to accelerate from 0 to 60, say 20 seconds, it tends to have less horsepower, generally speaking. There are exceptions, of course. We can see a couple little points here which don't really fit that. But it's a relatively strong negative relationship. So we can do this, and we can see how random relationships manifest themselves. Where random relationships aren't close to -1 or +1, they're actually close to 0. So here we have the relationship between miles per gallon, fuel efficiency, and mileage, which is just really a reflection of how old the car is. And as we can see, if we were to put a straight line through that, would probably come out pretty flat. So there's not really much of a linear relationship here, and hence it's close to 0. And the last one we show here is simply that this is a curvy linear relationship, and the line of least squares can't see curve, it can't fit curves, so it just goes through, just barrels its way through it as a straight line. It can't bend to accommodate it, even though here it's still a relatively strong correlation. It's really referring to how well the points cluster about this line, around about this section here. It's still coming out relatively strong negative correlation. If I just show you quickly where one might get these binary correlations, you'd simply go to Analyze and down to Correlate and down to Bivariate. I'm just going to pick one relationship here. I'm going to look at the relationship here in this data set between people's starting salary in a bank and the number of years of education that they have. And I'm asking it to show me the correlation between these two factors. And the correlation here is a positive correlation of 0.633. It's statistically significant, indicating it's probably not 0, and it's based on 475 records in the data set. If I wanted to represent that visually, of course, it would be a scatter plot, and I'll just go down here to scatter, and it doesn't really matter which one's in which axis. The correlation doesn't care. It doesn't have a direction to it in the sense that one's dependent on the other. That's something that comes in with linear regression. Correlation is no dependent variable, no independent variable. It's just the coincidence of them, if you like, or how they coincide with one another. So here's beginning salary and here's education level. And as we can see, yeah, education level, we don't tend to have it measured as like 12.5, 12.2, 13.1. They're integer values, so it's just 12, 13, 14. And we can see that, people tend to drop out at certain points, like, 12 years, 15 years, 16 or 17 years, 18 years. But there is a relationship here. Is it curvilinear? It might be a little bit curvilinear. It does look like it's kind of curving up here. We've got some values down here. But nevertheless, if we fit a regression line through that, a line of these squares, you can see it's kind of coming through like this. And it's giving me some values here which are really related to linear regression, which we'll come to in a moment. So our correlation for this value here is 0.633. What we can't tell from that is we can't interpret it directly as percentages. So we can't say, how strong the relationship is percentages unless we square the value. So here we have, for example, a correlation of 0.859, which is the correlation, the R value, the Pearson's R value between vehicle weight and horsepower. If we multiply 0.859 by 0.859, we get 0.738. And that equates to 73.8%. And that is called the R square value. And what that means is that if we imagine these as two circles which overlap with one another as a Venn diagram, we're saying that there's a 73% overlap between vehicle weight and horsepower. What do we mean by that? It means that 73% of the variation in horsepower can be accounted for by vehicle weight, and 73% of the variation in vehicle weight can be accounted for by horsepower. They overlap by 73%. In our case, back here when we were looking at education level and years of beginning salary, it's 0.633. Well, if it was exactly zero point 0.6 and we squared it, it would be 0.36 as an R square, so it'd be 36%. But it's 0.633. It turns out that that gets you an R square of almost exactly close to zero point 0.4. So that means there's a 40% of the variation in education level can be explained by beginning salary, and 40% of the variation in beginning salary can be explained by education level. The Venn diagram overlaps between the two groups, the two circles of variation by about 40%. And it tells us how much of the variation in one variable can be explained by the other. So the R square is simply the square of the correlation, and it's what is used in linear regression to measure how well a model fits or how well you can explain the variation in a dependent variable. So how do we express these linear relationships that we've discovered, that we've measured, that we've seen in using correlations? And we said that this is how strong this linear relationship is using correlation. It's 0.6, it's 0.3, it's minus 0.7, something like that. How do we turn that into a predictive model? Well, the simple answer to that is to ask yourself how long it takes to cook a chicken. Okay, so think about that simple question, how long does it take to cook a chicken? And you look it up in a recipe book, you'll often find that there are certain rules of thumb that people apply. So, for example, Julia Child says the rule of thumb is 7 minutes per pound plus 45 minutes added on. Whereas Delia Smith says 20 minutes per pound plus 20 minutes added on. Now, they may be setting the oven at a different temperature, so they're slightly under different conditions, etc. But they're both formulae, and they both have something in common in that they are both the formula for a straight line. And as we know, the line of least squares is a straight line. So we should be able to express the line of least squares, which is the kind of average of the relationship between two variables, or potentially more than two variables, as an equation. And because it's just a straight line, we would use the equation for a straight line, which is, depending on whether or not you're a mathematician or a statistician, is either y equals mx plus c or y equals a plus bx. Now, the letter on its own here, the plus c here, is the plus 45 minutes, and the a here is the plus 20 minutes. And the per pound bit, that's the coefficient, that's the m here, or the 20 minutes per, that's the b here, and the x is the actual weight of the chicken. So you can take this formula and you can pick up a 5 pound chicken or something like that, and if you're using Delia's recipe, well, 5 times 20 is 100, plus 20 added on to it, that means 2 hours you'd be cooking it for, effectively, because 120 minutes, isn't it? Now, we don't know what temperature and they're all that she's setting it at, but suffice to say, this is a kind of average, so it's a kind of rule of thumb, and this is how linear regression works. This is basically what linear regression is. It also means, of course, that if you take it to absurd extremes, it means that even if the chicken weighs nothing, you've still got to cook it for a minimum of 20 minutes. This constant is always added on. It's always a minimum value. So that tends to be when you're looking at the line, that often is the point at which that is the line, the point at which the line crosses the vertical axis. It's usually the minimum value in the y value that you're trying to predict. The y being the target, the revenue based on based on the promotion value, the promotion amount that you can spend, or the number of ice creams that you're going to sell based on temperature, or the amount of pollution you're going to see based on the average or total amount of rainfall that's fallen within the past previous 3 or 4 days, or however you measure it. Okay, so when we look at our earlier on, we saw the scatter plot. You remember the scatter plot? You're just going there it is. It's percent unemployed against public health care, and each of these is a US county. You can see that, look there, here's our line of least squares. It's drawn through that. If we then say, what's the formula for that line, that same line? Well, here it is. It's y equals mx plus c. So, or y equals a plus bx. It's saying, okay, if you want to predict, and the thing that you're trying to predict is usually in the y-axis, the vertical axis. And the thing you're using to predict it, the thing that creates the weight of the chicken, if you like, is in the x-axis. And if I wanted to predict percent of people in these states who are in these counties who are reliant on public health care using percentage of unemployed, I would take percentage of unemployed, let's say 15 here, and I would multiply that by 1.16. So it would just be a little bit above 15. And then I'd add on 10 on top of that. So let's say it comes to like 26 or something like that. So you can imagine 15 here. What's that read? If I read that off, is that about 26? Might be about 26 when I'm reading off from 15. So you can see that that's how we're getting that. So that is effectively the equation for the regression model. We don't know at this stage for this particular model what the R square value is. We don't know how strongly it relates to it, but I can tell by looking at the chart, it's going to be reasonably strong, and that's a pretty strong linear relationship that we're looking at there. Okay. Let's look at a demo of linear regression then in IBM SPSS statistics. Let's jump out and see how we do it. So I had this data set I showed you earlier, which is I had beginning salary, previous experience. I had education, which is the number of years of education that they had, and we discovered, but when we ran a analysis of that there was indeed a reasonably strong correlation between one and the other, 0.633. So if I was going to try and predict people's beginning salary based upon the number of years of education, having established the correlation, I might go to analyze down to regression. Note how many different types of regression techniques there are in SPSS these days. Lots and lots. The one I'm after is just called linear. That's the classic linear regression technique. And the dependent variable is the target, the thing that you're trying to predict. So in this case, I'm trying to predict what people's beginning salary is, their starting salary. And I'm going to do a simple linear regression. The thing that makes it simple is the fact that I'm only using one variable to predict another variable. And I'm going to run with the default settings. That's all I'm going to do is click OK at that point. And it just punches out default settings. So let me just hide some of these earlier. I'll hide some of this earlier stuff here so we can just look at this. So what you get is when you run the linear regression, you tend to get the same output, yeah, almost independently of whatever platform you're using, whether you're using SAS or using R or you're using Stata or Minitab or anything. It tends to be the same sort of output shown the same way. What you tend to get is, in this case, I'm getting information on which variables have been used, entered into it. Well, that's pretty obvious. It's saying I'm using education level. Doesn't tell me much. Then it gives me a model summary box. Model summary is telling me how accurate the model is. So it's basically the R value we saw earlier on. Remember, we saw that R value of 0.633. There it is, up here in the correlations. It is 0.633. It's just the R value. And what happens when we square that? Well, we get an R square of 0.041. Where did we see that? We saw it here, 0.041, which is the square of that. So it's telling me that 40% of the variation in beginning salary can be explained or predicted using people's number of years education. What we actually tend to predict, what we tend to quote when we're doing a research is we tend to quote the adjusted R square because the adjusted R square just takes account to a certain extent of the variation in the data and the sample size. It's kind of modified. It's always slightly lower than the R square value, but it's very, very close here, 0.399. If you got a reasonable sample size, they're very, very close to one another. But so it's still, I'm still going to round that up to 0.4, 40%. Standard error of the estimate is just telling me that on average, the error in this model is about $6,000 on average. And then we get this ANOVA table, this analysis of variance. Well, the ANOVA table here is a test of whether or not the model is actually better than basically just quoting the average. I mean, what is the average? I mean, if somebody said to me, you know, what do you think this person's starting salary is, and I knew nothing about them, I might just look at the mean and say, well, the mean's 17,000. So I'm just going to guess. If I don't know anything more about this guy, I'm just going to guess his starting salary is 17,000. So it's saying basically, is this better than just quoting the average? It's saying that 17,000. And it's saying, yes, it is. If that value should always be statistically significant. If these values here are pretty much anything above 1.1 or something like that, and if the model's showing anything, it's got any sort of R correlation at all, you kind of expect your ANOVA table to always be significant for that, always to be less than 0.05. And in fact, in this case, it's a lot less than 0.05, less than 0.001 by some margin. So this is kind of the critical bit here, the summary, telling me how strong the model is or how well it's explaining it. And then we get down to the next most important bit, which is the coefficients in the table. Remember, we have this formula that we've been talking about thus far. We said y equals mx plus c or y equals a plus bx. Let's go with that one. Those two aspects, the a and the b, they are shown here. Okay, here's the b value, and the a value is actually the constant. So it's just showing me that, saying if you want to predict how much somebody's starting salary is, or what their starting salary is, and how many years of education they have, then what you should do is you should multiply every year of education that they have. Let's say they've got 10 years of education by $1,728. So that's going to get you $17,000. Yeah, if I'm multiplying that. So $1,728. And then I take off. The constant is actually a minus number here, which is fine. You can have a minus number. You take that off, and it would take you down to about what, $11,000, something like that. So that's what we'd be guessing for somebody who had 10 years of education level. If they had 20 years education level, of course, it would be what, 30, $34,000 minus 6,000 or something like that, 6,300 odd. So, down to about $28,000 who take it. And we can see that they're both statistically significant. So we know that they actually contribute to the model. If you took them away, it would be detrimental to the accuracy of the model. That's what it's telling us, that the terms in the model, the B and the A, are significant. And then we get this thing called standardized coefficient beta. This is a correlation. Where have we seen 0.633 before? Well, there it is. It's just the R value, 0.633. Yeah, there's the R value. So this is how we can interpret it. Let's swap it out. Let's say, okay, look, I want to know somebody's beginning salary. I'm going to use something else here. I'm going to use something like age to try and predict their beginning salary. Does that help me predict it? Let's see if that works. Click OK. Swap it around. Okay, there's age. Look, the R value now is really, really weak. The R square is 0. And look, the ANOVA table's not even significant. So age doesn't help at all to predict somebody's starting salary. It's not statistically significant. And the constant is very close to the average. So it's basically saying, well, you might as well just use the average. It is statistically significant because it's closer than anything else. Might as well go for the average. Let's get rid of that. Let's try something else. Let's say I tried to predict instead somebody's current salary using their beginning salary. What would that look like? Oh, well, no, it's different now. The R square value is nearly 0.9. It's 0.88. The adjusted R-squared value is 0.77. Well, remember, if it was zero point 0.8 and I was squaring it, it would give me an R square of 0.64, wouldn't it? So here it's 0.88, so it's giving me an R square of 0.774. It's 77% of the variation in people's current salary can be predicted if you know their starting salary. And what it's telling me now is it's saying that if you take somebody's beginning salary and you multiply it by 1.9, that means that everybody's beginning salary is worth whatever your beginning salary is. It's worth $1.91, let's say, in terms of your current salary. So if your beginning salary was $10,000, then it predicts your current salary to be $19,000 plus, in dollar terms, 1,928. So you'd actually be adding on $1,900. So you'd be getting, nearly $2,000 added on there. So it'd be like, getting close to $2,100. The constant at this point is significant, but because it's playing such an arbitrary role at this stage, so really quite an arbitrary role, it's starting to get weaker because it's kind of like, yeah, and then stick on 2,000 at the end, kind of like almost as an afterthought. But nevertheless is statistically significant. Okay, I'm just run with this. Let's just swap that out. Let's not do beginning. Let's throw in education level. See if that helps. Is that a strong relationship? Well, now it's R square 0.661 against people's current salary. Oh, it's 43%. There's an R square. Okay, now what happens if I put both of them in? I'm trying to predict somebody's current salary and I want to use education level and their beginning salary. Well, remember, we know that there's a big overlap between education level and beginning salary. We know that because it's arguable that a lot of the variation in beginning salary is driven by your education level, isn't it? So the coefficients cannot be the same as before. They have to accommodate each other. They have to take account of each other because they're both kind of competing to predict current salary. And what I'm really saying is, what is the effect of your beginning salary on your current salary, assuming everybody has the same education level? Or saying, what is the effect of the education level on the current salary, assuming everybody has the same beginning salary? So it's kind of like this is called controlling for. It's where we're neutralizing the effect of one variable against the other. And when we run this, what we see is the adjusted R square value has jumped from previously the best we did was what? It was 0.774. It's only jumped a little bit, jumped to 0.792, so nearly 80%. 80% of the variation in one is controlled by the other. Of course, is statistically significant. And now we see that education level gets you, for every year of education level, will get you $1,000, and beginning salary now no longer 1.9 but 1.6. So every unit of beginning salary will get you $1.67 in terms of your current salary. Everything's statistically significant. But note that the standardized beta coefficients now, which are correlations I said earlier on, are now much weaker. Why are they so much weaker? Well, these are actually called partial correlations, and what we're saying is the correlation of education level against people's current salary in the present, controlling for beginning salary, is now only 1.72. It's much weaker. But the correlation of beginning salary against people's current salary, assuming everybody's got the same education level, would actually be 0.771. So neutralizing the effect of education level, this correlation becomes 0.771. Neutralizing the effect of beginning salary, this correlation here becomes 0.172. And for that reason, when you have two variables which are really, really strongly associated with each other, like correlations of like 0.9 or 0.88, they really don't they tend to mess up your linear regression. It's called multicollinearity. And you shouldn't have two variables which are really highly correlated with each other. And there are tests and statistics and things like that that you can do to try to work out. They're called collinearity diagnostics. Tell you if this is really a big issue or a problem if they're really highly correlated. I mean, to a certain extent, you just use your common sense and say, look, are they both statistically significant? Do they both look reasonable, even if it's quite a small number, quite a small correlation? If you go into statistics here, can I get collinearity diagnostics? Look at that. I'm not going to go into the details of them, but they're there. And just remember these collinearity diagnostics. If you double click on some of them, they'll give you like values here, like tolerance values here. So these tolerance values here. So you double click on them and say, what's this? It says it's a statistic used to determine how much the independent variables are linearly related to one another, multiclinear. In other words, how much, to what degree are they multiclinear? For the proportion of the variable's variance not accounted for by another independent variables in the equation. A variable with very low tolerance contributes little information to a model because it's so collinear with everything else and can cause computational problems that can mess up your model. It is calculated as 1 minus r squared for the independent variable, and it is predicted by the other independent variables in the analysis. And generally speaking, I think the rule of thumb is when that gets below zero point 0.1, you're kind of in trouble here. But here, as you can see, it's well above that. So it's when it's below like almost 10%, then you're getting you're getting into trouble here. Here's perfectly healthy. Even though education level's not bringing that much to the party, it brings enough. It's doing well enough. So let's run this again. Let's add in some other variables. Let's go to statistics. I'm just going to switch off these collinearity diagnostics. You can notice you can add in things like confidence intervals, you can look at the change in R squares and stuff like that. There's lots of other different tests one can do here. I'm going to put in months since hire and previous experience. We know age doesn't do anything. I could even put in things like minority classification because this is called dummy coding, which we can come to in a moment. Click OK at that point, and it runs that. Okay, so it's dummy coding. Um, and here we have, yeah, we can see that is everything yeah, everything's statistically significant, but it's the law of marginal returns. Notice that previous experience actually has a minus number attached to it. It's weird, isn't it? A minus number saying that the more previous experience you have, you actually get $17 on average less. Why would that be? Well, because some of the people with the most previous experience are actually people in the lowest paid jobs because they're some of the oldest people and they work in things like the custodial group. Month since hire, every month since hire, you get an extra $161. So we're really directly interpreting these values in terms of the units that the dependent variable is measured in. I mean, here we see the adjusted R square here is only going up to 0.809. You can do fancy stuff like this is called the enter method where we're forcing them all in. You can do stuff like forwards and backwards. If I did forwards here, it would build it up step by step, adding in each significant model, each significant variable. So you can see it actually creates 4 models each time adding a variable. And you can see it starts at 0.774, 77%. By the time we've added another 3 variables, it's only climbed 0.809. Some people would argue that the difference between 0.803 and 0.809 is so small that it's not contributing much. Other people would argue, yeah, but that might help explain some weird and one or two individual cases which are a bit odd, you know. And we can see that the ANOVA model is always significant as the model's being built each time, model 1 through the model 4. And we can see the coefficients here being shown. So look, I can double click on that and I can say, put the model into the nested group here. And look, there's the first model, beginning salary going in. Here's the second model. It put previous experience in months going in. Look, the coefficient now changing. If we put another variable in, it's like months since hire goes in, 173, and put in a fourth variable. The values are changing, of course, as we add in more variables because they all correlate with each other. The last one is education level in years. So all of these variables go in. And that's called forward stepwise. You can do backward stepwise. It's kind of like the difference between building a house of cards, which is what forward stepwise is, or Jenga, which was where you put everything in and it takes out only the non-significant ones, trying to leave the model as significant as possible. Look, there's a few other things you can do here. There's something called dummy coding. Have I got time to touch on it? I'm going to touch on it very quickly. Um, have I got something? Yeah, I've actually got a little procedure here called create dummy variables. I'm going to show it to you. Let me do dummy coding. I've got a variable here called employment category. That's not a number field in the sense that, it's just a category field. So it's a category field, and the categories here refer to, are you a manager, a clerical worker, or a custodial worker? And they all have very different, they all have very different salaries, of course, associated with it. Um, if I just looked at the average salaries here and said, let's compare means, let's go to compare means, compare means. Where's means, compare means, compare means, there you go. And I said, let's look at the current salary and broke it up by employment category. You can see the average. Look, this is a clerical workers on average earn 27,000, custodial 30,900, and managers 63,000. So I can't just put that variable into a linear regression equation because they're a set of categories. They're not, it's like putting ethnicity in. I can't say every 1 unit change earns you an extra $5,000 because I don't know if clerical's higher than custodial or custodial's higher than clerical or something like that. So what you do is you can do something called dummy coding here. And here, dummy coding just marks down whether or not you're a clerical worker or not. 1 for yes, I'm a clerical worker. 0 for not, I'm not a clerical worker. And 2 here is 1 for yes, I'm a custodial worker. And 2 and 0 for no, I'm not a custodial worker. And the third one is managers. Well, it turns out that if I just put 2 of these in, I don't need to put the third one in because the third one will effectively be the constant. If I run this again, I'm just going to put clerical and custodial in. I'm going to leave manager out. This becomes what you call your reference category. You'll see another example of this. Let me just force them all in. Click OK at this point. And what it's saying is that clerical worker earns you 10,957 less. Less than what? Less than a manager, because the manager is effectively the constant. That's the reference category. Custodial earns you what? Is that $3,101 dollars less than being a manager? So we dummy code these. We can add these categories in. You could do this with ethnicity, with region, or something like that. You just leave one category out. It's called dummy coding, and it allows us to add in a uh, a variable by breaking up into categories and allows us then to predict outcomes, just make some binary categories, dummy coding. Notice that custodial here is not statistically significant. We don't need to use that one in there. It's not contributing much. Okay, the last thing I just wanted to do here is let's say I built that model there. I'm just going to delete this. I'm just going to go back and I'm just going to just run with this original model that we had. So this model here. Notice that what I can do is if I look at down at the bottom of this data set, I've actually got a last category here. Look at this, the last record here where we don't know their current salary. It's missing. Well, one way in which we can predict it is if I go to linear regression and I say save, I can just say save unstandardized predicted variables, predicted values, or predicted variables. That just means raw. If I double click on that, it shows me this big long number. That's actually salary. And I can actually just clean it up a little bit here. Make it 0 decimal places. Let's change it to dollar, just to make it absolutely clear. That's the dollars. Look, that's the number of dollars it's predicting them to be. And if I go down to my last category here, we don't know what this person's salary is, but we can predict it. It's predicting it for us. Look, $26,000. It's using the remaining values where it does know their salary to build a model to predict it. So you can just add extra rows onto the bottom here to predict it. The alternative approach is to save the model. Some of you have seen me do this in the earlier on when I did decision trees. And I can save it out and say, I want to save this model out. I'm going to call it employee linear. Look, I've already got it there. I'm just going to say, save that. Employee linear, hit continue. It saves this model out. And then I open up a brand new data set here called the employee unknown current salary. Just another data set. And look, it's the same data as before, but the salary is completely missing. We don't know what the current salary is. So what do? We use the model that we saved and we go to scoring wizard. We pick up employee linear, which is the model we saved. It maps the fields, the predictor fields, the independent fields across, and it says what do you want me to show? And I'm going to say predicted value, actually predicted. Let's change this. Predicted current salary. Okay, and hit next and finish. And it applies that model to it, and we can make that dollars, of course. And then we applied the model to it. This is how we can port the model. Okay, that is linear regression. What about, we did talk about logistic regression. We just got 15 minutes here. We've introduced linear regression. It's much easier to understand logistic regression if you've already seen linear regression. Logistic regression is used when you want to predict a category outcome. So logistic regression allows us to predict things that linear regression can't, such as response to a marketing campaign. Linear regression will understand that you're trying to predict like a 0 and a 1, and it can only be one of these two categories, one of these three categories. It just thinks you're trying to predict a number that could, run from minus infinity to plus infinity. Or credit risk, whether or not somebody's actually a good, is going to pay you back if you lend them money. Or whether a subscriber is likely to renew a Netflix subscription, or the risk of equipment failure. It's used a lot in patient predictions, used not whether or not a patient will survive treatment or will be readmitted to hospital, or whether a charity donor will switch to debit card, make direct debit rather than casual cash donations. So anything where we've got a category outcome, and as a result of that, it's an extension of linear regression. These outcomes are not continuous numbers, so standard linear regression won't work. And when the outcome consists of two categories, as I say, we call it binary logistic regression. When the outcome is three or more categories, we call it multinomial logistic regression. Logistic regression gets around the limitations of describing relationships of straight lines by using a special sigmoid curve. So this is what logistic regression sees. Statisticians generally approach things by trying to find a curve that reflects that situation. And if you wanted to reflect a situation where you've just got a 1-0 outcome, a good curve to use for that is like an S shape, because you've got like two conditions, the top and the bottom of the S shape here. Let's imagine we were selling iPhones, and we're selling them off our little website, and if we don't offer a discount at all, nobody's going to buy. Nobody's going to buy from us, because why would they? Why don't they just buy directly from Apple? If we don't have guarantees or anything, we're doing warranty. Why would you do that? If you start to offer a discount, though, probability of responding to our offer, gets better and better. So as our discount increases, maybe to 100% discount, everybody's going to order it, of course. So the probability of responding goes from 0 to 50% chance, 60% chance, 70% chance, 80% chance, 90% chance, 100% chance. And this is what logistic regression is doing. Now, given the fact that this is a special situation, we can't talk about it in linear regression terms. We can't say a 1 unit increase in the discount increases the probability of by 5%. Unfortunately, it's not quite going to do that for us. It doesn't work that way. It actually works with logs, not with probability. So the logs are related to odds, the odds of somebody actually responding. So what it's going to do is it's going to create an axis along here. It's not really going to have the discount in percentage. It's going to create these numbers. Very like y equals mx plus c. In fact, it uses this formula, but it produces these numbers here, the coefficients, and these numbers push the probability along. And there's a special formula that converts these numbers into probabilities. The formula is called the logic conversion formula, or link formula. It's basically, for the record, it's 1 over 1 plus e to the power of minus z, where minus z is these numbers. So basically, so whatever they are. So these are kind of abstracted numbers, but you could calculate this by hand, and you could calculate the probability of people responding manually if you so wished. Let's look at an example. It's easier to see. If you look at an example, I've got a little data set here called News Channel for Logistic. And the idea is it's some old data. I'm just going to close down the output here in the background, because it's just going to confuse us. We've got this variable here, which is, did somebody subscribe to a new news channel service? So let's say it's like a new, I don't know, streaming service, something like that, News 24 or something like that, Some people or subscribing to it. 48% of the people in the sample subscribed to it, 51% didn't. Okay. And we've got these factors here. So we can't use linear regression to predict this outcome because it's a binary outcome. So we're going to use logistic. So let's go to analyze and down to regression, to binary logistic, which is what we're going to use. This time, instead of saying dependent and independent, it says dependent and covariate. That just means numbers. And if I pick up, say, accept news channel, that's my dependent variables. Binary, it expects there only to be two categories in there. And I could pick up age and years and put that. I'm just going to put that. I'm going to do a simple logistic regression. And if I click OK with just the default settings, you'll see that what we get is two models, one called block 0 and one called block 1. So it starts off telling us that it says, look, I predict nobody to be in the S group. Yeah. Why is it doing that? Well, because there's more people in the no group than the S group. So it's saying that if I don't use any variables at all, this is kind of like the average that we saw earlier on in linear regression. It says, well, I might as well just predict everybody being in the no group because there's slightly more people in the no group than there's in the S group. So it's kind of a reference point. It's kind of saying, look, you got to beat this. This is what you're trying to beat. So the variables in the equation are just the constant. The constant is just basically relates to a 51% chance of you being in the no group. That's all it is. It's just an abstract number that you could put through this formula and it would give you a probability value of 0.51 of being in the no group, and everybody would be predicted to be in the no group. That's what it would be doing. And it says the variables that aren't in the equation at this stage is age and years, and it's statistically significant. And it tells you there's an omnibus test, just like the ANOVA test we saw earlier. And it says, okay, if we put this in step by step, if you put this in separate blocks, if you created separate models, they'd all be statistically significant at this point. That's just basically saying this will make a statistically significant difference to the model when it's added in. And then it gives us model summary values. Now, it doesn't give us nice R-square values. It gives us what are called pseudo R-square values. So there's one called Cox and Snell and one called Nagelkirk. Okay. And as you can see, the R-square values are always pretty weak. 0.1, about 10%, 0.14, about 14%. You could actually have a really good model with quite small pseudo R-square values, but they're just an attempt to try and get something more familiar for people to look at. The true value is of model fit is usually regarded as the -2 log likelihood value, but that's so abstract. You can't really interpret it directly. It's just -2 times the log likelihood. That's just too abstract. But suffice to say that the smaller that number is, the less error there is in the model. So if you really want to compare one model to the next, you could look at the -2 log likelihood. And then it tells us that after building the model, this is how accurate it was. It says, if we just use age, I'll be 74% accurate at predicting people in the no group, and I'll be 53.7% accurate at predicting people in the S group, which overall means I'd be 64.6% accurate, which is better than our baseline of 51% accurate. So it does make a statistically significant contribution. And then we get our coefficients again, our y equals mx plus c, but this time the m and the plus c, they don't really mean much. They're too abstracted because you've got to put them through a formula, and what they really refer to is the log of the odds of being in the response group. The response group being whatever that is, the higher number. The higher number is yes. That's the the internal coding. So it's the log of the odds of people being of responding and accepting the news channel, and they're both statistically significant. So we can't really say much about this, but what we can say is the constant's negative, and we can say age is positive. It's a positive value. So age, the older you are, the more likely you are to to buy the service. So what's interesting is we can see age is significant, constant significant. We do have this value though. This is this value, but it's called xb. It means exponentiated b. It means it's been raised to the power of the exponent, which is like a value like pi. And it's saying that for every 1 unit increase in years, the odds of you accepting the news channel increase by 1.05. Now that doesn't seem like much the odds only increase by 1.05. But that's because age has got a lot of values, and every 1 unit increase in it affects it. If I actually, if I actually just illustrate this, I can go to visual binning and say, let's take age here, and I'll just create a three group age variable for it. I'm going to call it age three group. Yeah, just call it three groups. Just it's going to be three groups. We're going to take age. I'm going to split it into three groups. And we'll use that instead of the original age. And I'll say make cut points. And it does that. And I'll make labels for me. There you go. The three groups up to 33, 34 to 44, and 45 and over. That's the three age groups. It creates that for me. And I can use that instead of my original age. So I'm using this. But that's kind of an ordinal variable. And now we get exactly the same, pretty much the same results as before, even though the data's changed a wee bit. But it's basically saying for every 1 unit change as you move up through the three age groups, the odds of you accepting the news channel increase or double, more than double. Okay, so that tells you the effect of the units that you're measuring the thing in has on the outcome. So because we've only got three age groups rather than, you know, 60 different individual age values, it's really showing us the effective age. And if I went back here and added in other variables like how many hours you spent watching TV per day, education levels in years, and I could put in gender here. Gender here is coded as 0 for one and 1 for female. So the female would be the reference group because that's coded as 1. If I click OK, that's basically like a dummy code. What we can see is age and years is significant. Hours spent watching TV per day is not significant. Doesn't help us predict it. Education level is significant. It's positively related. Every year, if education increases the odds by 1.09. And gender, the effect of not being a woman, basically. Oh, sorry, the effect of being a woman, which is our target group here, it decreases the odds by 0.5, so it halves the odds. I could swap this around. I could actually change this. If that's confusing for you, I could go in here and categorical and say, here's gender, and the last category is my reference group. That's males. And you can see here now it says the effect of being a man versus being a woman actually increases the likelihood of subscribing to it, nearly doubles it. Yeah. And I could get rid of the non-significant TV hours per day. Click OK at that point. And now the accuracy overall is 68% accurate in predicting the no's, 63% accurate in predicting the yeses, 66%. And if I asked it to save this model and save the scores out, what it's actually going to save is the probabilities and the predicted group membership. So it could take these values here, these y equals m, put them through a formula, and it would tell me the probability of being somebody who buys the news channel. So it's saying here, look, there's a 70% chance to buy the news channel, so I'll predict them be a news channel. There's a 21% chance they'll buy the news channel, so I'll predict them not buy the news channel. There's a 63% chance they'll buy the news channel, so I'll predict them to be the news channel. So if it's over 0.5, you get a yes, and if it's below 0.5, you get a no. Yeah. And there's lots of charts we can do to explore this and look at it in more detail. So it is an evolution for a step on from linear regression, but there is some familiarity there. It's just that there's some sort of abstraction here with regard to how we interpret the coefficients, because the coefficients, they're not necessarily intuitive. But then the result isn't a linear number. It's actually a probability of being in a category. Bear in mind, SPSS has a lot of regression methods, and the regression module adds several key methods like logistic regression. If you just want to do linear regression, you don't need the regression module. But if you want some of these other regression methods, you'll need the logistic regression, you need the regression models module. Many additional methods are also available through the SPSS's integration of R and Python. You should be aware of some additional resources here. I have little videos on how to model nonlinear relationships, something called moderation analysis, mediation analysis. And you can find out, what if you want to find out if you've got regression models, you can check that, see what's included in it. And also a little blog series here on on statistical tests and procedures. You should also find I've got a new video on our YouTube channel looking at Poisson regression as well. So that might be interesting. Okay, just so you're aware that we do have a portfolio of online training materials that are free to our existing customers or available for purchase for non-existing customers. With regard to working with Smart Vision, we offer a range of different training options and consultancy options, including things like a mix of consultancy and training, whereby we do the initial work and then teach you how to replicate it. And you can work with us. You can buy your analytical software, your SPSS software directly from us. We even have our own web store. As I say, we offer training consultancy service, and we also offer no strings attached advice to anybody that comes to us with technical or business advice within analytical activities. And people who already have it with IBM and want to switch their license to us, they can do so, and they can avail themselves of our free software, or sorry, our free training and other software and other services, as well as our direct technical support services, because we've dedicated formal technical support. In the meantime, I hope you found that useful, and we look forward to you logging in again in the future.